Hello, everybody. I hope you have had a nice day so far. Just so you know, it's the third time I'm recording this video due to some technical issues. No worries. So, following the course and our last session talking about particles characterization, we said there are four basic characterizations or some four basic characteristics of particles, including size, shape, composition, and structure. And we mostly talk about size and size distribution of the particles. Today, I want to discuss more about not only size but also composition, structure, and shape of the particles with some advanced equipment that are practiced in industry and in academia. So first, let's talk about chemical composition. In terms of chemical composition, we have assay methods in order to have elemental composition or elemental characterization of the particles and uh, analysis of the particles or in order to understand the mineralogy of the ore. Or in other words, what are the chemical compounds or chemical or compound chemical compound form of the metals or any element of interest. In terms of assay methods, there are some equipment like NAA or neutron activation analyzer, XRF or X-ray fluorescence, reduced coupled plasma or ICP with different detectors such as AES and MS, mass spec. These methods have advantages and disadvantages. For example, with NAA and XRF, you can analyze your samples in solid form, but with ICP, you have to dissolve your sample, so your solid sample into acid, and at the end, you should use a liquid sample for ICP analysis. Another difference between each technique is, in fact, um, uh, detection limit of each equipment. For example, if you have metal of interest with a very, very low concentration, ICP, MS, and or NAA is better or better. And if you have some samples where the element of interest is at uh, high enough concentrations, XRF is good enough. This is a good example of assay data from a phosphate ore from Morocco. Uh, you see that all data are reported in ppm for elements. There is nothing here about chemical compounds of the element. So this is called elemental assay. Now I want to talk about one of the very advanced equipment that is called quantitative evaluation of minerals with the scanning electron microscope or chemoscan. This machine is in fact uh, a kind of electron microscope. I don't know how or to what level you have heard of SEM, scanning electron microscopy. ChemScan is basically SEM with a special microscope detector. And this equipment has been used for several industries, for base metal, for platinum group metals, heavy minerals, sands, and many other applications. Something I want to emphasize now before I move to other slides to tell you what kind of information we can obtain by ChemScan is about sample preparation. In fact, I had to talk about sample preparation also when I talk about uh, chemical assaying. Regardless, always you have to make sure that you obtain a very reliable sample of your ore particles because especially they are very heterogeneous from particle to another particle, from one location of, let's say, mine to another location of the mine, or from one country to another country, ores are not similar. And if you have a situation that you have sample from different locations and you have mixed them, you have to make sure that your sample is prepared in a very reliable manner, as we are discussing in the course. ChemScan, in fact, works based on uh, backscattering imaging. Backscattering imaging is a technique by SEM. You don't need to know exactly what it is, but if you're interested, you can go online and search for it. With ChemScan, you can identify characterization of the particles down to 15 micron. In other words, if you have nanoparticle, it's not a good machine, but immunoprocessing processing is good enough usually. And by ChemScan, in fact, you end up with particles with different, with the surface, with different darkness or brightness levels. You have particles with a very light surface, and you have particles with darker surface in a kind of gray scale. How, and if you just consider this one single particle from these ore particles, you can see very clearly that in gray scale you have different colors. This is almost very black, and you have some small white color and then gray colors. So what ChemScan does is that it has a software with complicated mathematical modelings. So based on its database, it can identify uh, each single mineral that has caused these color changes, and subsequently, ChemScan allocates a very identifiable color for to each mineral. For example, if you consider this single particle, uh, chemists can identify four minerals of pyrite, silicate, talentite, and chalcopyrite with different colors. You can see in this picture and also in other pictures that, as we discussed in the class, particles are not spherical; they are very irregular shapes. And so not only you with ChemScan you can really identify different shapes. Also, you see they have different compositions. For example, if you just look at the purple color, purple here is more, but less than purple color here, even though it is a two-dimensional picture. In this particle, you don't have pink color, which is silicate, but here you have it. And also in terms of structure, you see that um, you have the way that minerals are associated together, which means how minerals are beside other minerals, they are not the same thing. So even in terms of structure, they are different. So these are very primary information that you obtain from ChemScan. But based on all these basic and primary information, ChemScan can give you much more information in terms of modal distribution of minerals or total mass fraction of minerals in your sample. In terms of grain size means, for example, what is the size of the mineral, each single mineral in a particle. Okay, it can give you many other mineral processing information in terms of mineralogy that are helpful for making strategic decisions and designing your unit operations. For example, one of the important information that the chemist can give you is the grade recovery curve without doing any experimental work. I will show you later on how it works. ChemScan has to verify the results are reliable. So, before doing ChemScan, we have to apply a chemical assaying work by ICP, NAA, XRF, whatever, and then compare the data with the assay data that ChemScan calculates theoretically. And as the case here, data experimental assay data and theoretical assay data should be consistent. Otherwise, reliable data of chemistry are not reliable. Now, let me show you some typical and interesting data that you can obtain from chemistry. Consider a lead zinc ore with different samples of A, B, C. So similar ore, they are PBZN ore, but different, for example, from different locations. But imagine here, all three samples have similar size distributions. Minus 600 plus 3 means particles above 3 micron and below 600 micron. By just considering these similarities, we see that ChemScan has identified modal distribution of the minerals in the ore with different chemical compositions, with different mass fractions. For example, mica exists in sample A, but samples B and C they don't have mica. In other words, maybe for sample A, we have to apply a special separation method to remove mica, but this unit operation is not necessary for samples B and C because they don't have mica. So you can see by having this kind of uh, composition structure of the mineral, or in other words, by this kind of mineralogical information, you can decide what you have to do for your process. Because we know in mineral processing, a big purpose is to make a concentrate, is to get rid of the gangue and recover the most valuable mineral. This is another information about grain size, mean grain size, okay? Because as you saw in our other pictures, grain of the mineral in each single particle has different sizes. But this is the mean average size, and each sample has different. Uh, in each sample of ABC, minerals have different grain sizes as well. For example, pyrite in sample A is 170 micron, but in sample C is 109 micron. What it means? It means, for example, if you are working with sample A, maybe you need to apply grinding uh, until particles have a kind of average size distribution around 170. But if you want to separate pyrite from C, you have to grind more, so particles are smaller in order to liberate pyrite from sample C. Now that we talk about liberation, let me tell you what it means in terms of liberation or in general association of the mineral in mineralogy. Imagine that the mineral of interest is this red color. If surface area of the red color, or anyway, our mineral of interest is free, uh, I mean, almost without association to any other mineral, and the value is more than 95%, we say the mineral is a free mineral. But when this surface is free for something between 80 to 95%, we say the mineral is a liberated mineral. And for lower levels of this free surface area, we have middlings, submiddlings, and log. You can see, for example, in this case, the red color is almost fully surrounded by the pink color. It is fully locked. So you have to cut it from different angles in grinding or crushing so that the red color can be eventually free. This picture is about a copper ore, a copper mineral, Cu porphyry. And we have here a ChemScan analysis of four samples of the same ore. First sample is just a sample that we have grabbed from ore, and the other three are after we apply sieving to our sample. So we have received two particles below 20 micron, between 20 and 75 micron, and particles above 75 micron. This graph shows you that by having different size distributions, okay, you can see that uh, composition and structure of the ore particles is very different, not only from each other, but also from their mixture before sieving. For example, this copper sulfide in free form is about 78% in size class of minus 20 micron, but above a bit higher than 40% for particles of 75 micron and more. So it's very important that so this information here tells us that particle size distribution is extremely important in mineral processing. And beside particle size distribution, that you see the clear difference in terms of composition, the structure is also not the same. For example, association of the CUS, for example, here to mica in whole in the combined sample is about 6.8%, but for example, here, for in this size class, is 8.9%. And you see there are different associations here. So in terms of structure, they are not the same. This last slide that I want to share with you is about uh, theoretical recovery and grade scenarios that are obtained from ChemScan for 4 different samples. Uh, a sample without sieving, and 3 samples after sieving were applied to a copper ore. You can see that theoretically we got results as we expect. In other words, if, for example, we want to have a copper in our product stream with a purity of 30%, we, we can realize that we will have a recovery around 95%. But if you want to have higher grade, higher purity, let's say, for example, 60%, and if you work with these larger particles, your recovery will be just above, just a little bit above 60. And if you want to have very high recovery, like 100% recovery, your grade is almost useless, just 2% maybe. So these data are obtained by ChemScan, and these theoretical data are compared with experimental data. You see that they are, even though in terms of size distribution, are not the same, because experimental data were for particles below 53 micron, different from these ones. But still, the trend is consistent. But the message here is, by having these recovery and grade information from ChemScan, you save a lot of money as engineer. You don't do a lot of sophisticated and expensive pilot testing or lab testing to identify what is the grade and recovery that you can obtain, and then subsequently design your unit operations. You can upfront do chemistry analysis and get already a lot of information and save time. I hope this presentation on assay methods and ChemScan analysis was useful for you. So if you watch this video and have more questions, don't worry, I'm here for you, and just let me know. I wish you all a very nice day.